Welcome back, everyone. Our next speaker is Colleen Robichaux talking about deciding Schubert positivity.
Yeah. Thank you so much for having me. Is my sound okay? You can hear me? Hopefully. If I won't be able to see the chat, so if there are any questions or comments, either someone will have to, tell me, or just unmute yourself and feel free to ask a question. But today I'm going to talk about some recent work with Igor Pak, in which we're studying the problem of looking at when a Schubert structure coefficient is positive using the perspective of computational complexity. And so just to make sure everyone is on the same page, we'll start with defining what these Schubert structure constants are. And so for that, we'll talk about Schubert varieties. So we'll start our journey with the complete flag variety. So this is the set of all complete flags in Cn. So by complete flags, I mean we'll start with the zero vector space, and then we're going to build up to a one-dimensional vector space, which is inside of a two-dimensional vector space, adding up sort of one dimension at a time until we build up to Cn. So here's a little picture that you can think we have, a point that's lying in a line, that's lying in a plane, which is lying in the whole space. Okay. And in a point in the flag variety, we could look at the group orbits of the Borel subgroup, and there are going to be naturally finitely many orbits. They're going to be indexed by permutations in the symmetric group, and these are Schubert cells. And the Zariski closures of these cells are the Schubert varieties. Okay, so we have these Schubert varieties living in the flag variety, but you can also just think of these Schubert varieties as just being families of matrices that we've sort of grouped together according to their pivot structure. Okay, and so one question that you can ask about these Schubert varieties is you could try to intersect them. Okay, so if we have these, let's say, three Schubert varieties indexed by permutations U, V, and W, maybe I'm interested in studying these intersections in the cases when we should expect their intersection to be zero-dimensional. So there's going to be some number of points in general in the intersection of these three varieties, where I'm going to sort of perturb each of these copies by something random to make sure that I'm getting some sort of general picture of what these intersections should look like. And so you can study what should be for U, V, and W, what should be the number of points that you would measure in this intersection. And something that's not obvious is that if you have indeed sort of perturbed these Schubert varieties by actually generic elements in GLN, so actually chosen sufficiently random things to perturb these varieties by, you're always going to get the same point count here. And so since this is a well-defined question, we could ask, how can you find other ways of computing these intersection numbers without actually just solving a system of equations, right? What might be a more elegant way to compute these intersection numbers? And so that leads us to some central questions in Schubert calculus. So first, right, we know that these, I'll call these Schubert structure constants here. And right, we know that they're non-negative integers because they're counting some number of points in this intersection. And so we could ask, could you find a combinatorial rule to compute these coefficients that is manifestly positive? Where by manifestly positive, I mean that when I'm carrying out this combinatorial rule, I only want positive contributions of this rule. I don't want to have some things that are associated to a positive weight and some with a negative weight where you could get some cancellations. So I want just some nice positive way to compute these coefficients. So an example of a manifestly positive combinatorial rule would be like the Littlewood-Richardson rule. That's counting these same intersection numbers, but in the Grassmannian. Okay. But in general, this problem is very hard, it's very open, and it has been proven in some special cases. So for particular families of U, V, and W, we have manifestly positive combinatorial rules, but in general, this is very open. And so it might be natural for us to consider a coarser question. So rather than asking for a combinatorial rule to actually compute these coefficients, we could instead ask for some combinatorial algorithm to decide when they're positive, some efficient algorithm to decide when they're positive, maybe. And so this is the question that we're going to focus on today, this problem of just deciding when this intersection is non-empty, okay? Or equivalently, when is this coefficient actually positive? And I said I was thinking about this question through the perspective of computational complexity. And so I'll give a sort of brief overview of how some of these concepts are fitting together. So the type of problems that we're really talking about in this context are called decision problems. These are problems where the question that I'm asking just has a straightforward yes or no answer. Might not be easy to obtain that answer, but that's just the style of question that we're asking. Okay, so for this bottom class, these are all just classes of problems, where as you go up, this is inclusion of these classes. So here at the bottom, I have P. And these are the problems that it's polynomial time to obtain that yes or no answer. Okay, so I could have the problem of asking, is this graph bipartite? I could give you the graph and ask you to tell me if it's bipartite. And that's going to be polynomial time to decide. Okay, but if we go one level up, we have the class NP, which stands for non-deterministic polynomial time. And these are problems where you can check some evidence that the answer is yes in polynomial time. So a problem that's sitting in here would be like 3 coloring of a graph. So it might not be easy to, from scratch, come up with a 3 coloring, but it's easy to check. If I hand you something that I tell you is a 3 coloring, it's easy for you to check that it is. And then we can keep sort of building up. We can go one level up in the hierarchy here. And these are the problems that you can check evidence of yes in polynomial time if you can cheat and look at a 3 coloring problem in unit time. If you have a cheat sheet that lets you look up the answers to that one problem, then you'll have problems in this next level of complexity. And you could keep building up like this, looking at answers to problems that are one class lower, and you'll build up the polynomial hierarchy, this PH. Okay, and so all of these things are to do with time complexity. You could also look at space complexity. So maybe you don't care how much time it takes you, but you're restricted to only polynomial amount of space, and that's P space, and that's living all the way up here. So this is our general starting framework for how we could try to think about where should the Schubert vanishing problem be living here. Okay. And when we start out, really the best that we know is not even in P space of where the decision problem should be living of is this Schubert intersection empty or not, it would be in exp space. So all the way up here is where we would start from. Okay, but this problem has been well studied. And the issue is that while there are some nice characterizations that are easy to carry out to decide in some cases that we all know it's vanishing, or some cases that we know that the coefficient is positive, the problem is these are all partial characterizations. So no single one of these characterizations can tell you all of a perfect if and only if characterization, nor can you patch them together to get a full characterization. Okay, but these, just to give a bit of context into the flavor of these, so this first rule of Knudsen in terms of descent cycling and Kevin Prabhu's in terms of root games, these are looking at the structure of the permutations themselves. And just from these permutations, you might look at some of their inversions, things like this, to in some cases be able to predict that the coefficient should be positive, in some cases predicting that the coefficient has to be 0. Okay. Then another example is Billy Vauquel's more geometric flavored rule that's using these Erickson-Linnesen permutation arrays to decide whether a coefficient has to be 0. And we could look to another rule of St. Dizier-Yang, which is looking at a more polytopal way of deciding when a coefficient has to be 0. But these aren't perfect characterizations. And so, we've had a lot of people working on this problem, but no full characterization that necessarily seems combinatorial or necessarily fast on its face to carry out. And so we can sort of, we're this guy at the bottom, and we have to figure out what we want to do. Do we think that there actually exists, right, a nice rule, a nice polynomial time rule, or an efficient rule to carry out to actually decide whether these coefficients are vanishing? And so we could sort of go one of two ways here. So we could go the sort of negative route following these dark storm clouds and try to prove that the problem is hard. So we could try to prove that the problem is sort of outside of the polynomial hierarchy, is as hard as can be, and so that we should never expect that there's going to be a nice answer to the question. Or we could go the positive route and try to actually find an efficient algorithm to decide Schubert positivity. Right. And so starting out, we were actually trying to go this very negative route, and we kept failing at right, showing that this problem was provably hard. And so we backtracked and decided to try to go the positive route, and that turned out to bear fruit for us. And our first step in this journey that we took was, right, we kept failing in trying to prove that the answer to this problem was hard. We couldn't prove that it was very, very hard to decide the Schubert coefficient was 0. And so we sort of zoomed out a bit and said, okay, there has to be extra structure to this problem that we're not taking account of. So let's look at what is the fundamental structure to this Schubert problem that we can really zoom in on and distill down. And so what is some of the most fundamental structure to the Schubert problem is the algebraic structure, right? This Schubert intersection is defined as some, it's going to be a point in this intersection is going to satisfy all of the equations determined by those 3 Schubert varieties. That's exactly what it means for one of these, for a point to be in that intersection. And so we could look at this class of problems called Hn. That is the decision problem of saying, okay, I have this input system of polynomials where I don't have too many polynomials, and these polynomials are sort of small to represent. And I could ask the question, does this system of equations have a complex solution? Okay, that's just a family of problems that's natural to ask. And in general, right, that problem, if you're not using too much cleverness, it'll be an exp space. So before you do anything clever, it's even using Grobner basis techniques, right? You don't get too far. Even using the effective Nullstellensatz, you get up to P space. But in 1996, Quaram had some landmark work in which he showed that Hn is in this class AM, assuming GRH, where if we apply some fancy computer science assumption, his result would say that Hn is in NP if we assume GRH, the generalized Riemann hypothesis. Okay, so I don't think maybe in question time we'll have time to maybe talk about the GRH part if anyone's curious about it. But this would say that the problem of asking if a system of equations has a complex solution, I should be able to actually check evidence of that in polynomial time. Okay, the quirk is that, right, you would hope that you can just plug in the solution to that equation, right? If we are claiming that there is a complex solution, you would hope, okay, well, the NP test is just plugging in that solution. But the issue is, depending on the computation, right, that solution that you want to plug in, you need it to be easy to represent, small to represent, and you have to be able to plug it in and check everything quickly. And that's where the subtlety is in obtaining this result. And so, right, we look at one formulation of the positivity problem, right, that was characterized by Heinz et al. They gave some equations that are cutting out the points that are in the intersection. And separately, we could look at some equations that Kevin wrote down that are characterizing when the coefficient is going to be 0. And that gives us the fact that this result is going to be in NP, so we'll be able to easily check evidence of a yes answer, and we'll easily be able to check evidence of a no answer in polynomial time. So we're in this class NP cap co-NP, where we do have to assume GRH. Okay. And this technical computer science assumption to get in this NP class. Okay, So we took the sunny side road, and we got that this should be in this class NP cap co-NP, but we have these two very hefty $1 million+ assumptions along for the ride. But this gave us hope that we could actually try for something more. Okay, but what we have to do is just be okay with maybe being wrong sometimes, right? It's a good lesson in life, being okay with being wrong sometimes. And so what do I mean by that? So this is the part of the hierarchy that we had to start out with. And without our weird computer science assumption, we had shown that our problem is living here, assuming GRH, which is inside of the hierarchy. But the thing about this class, this class here, which I'm not going to define, it's a class of interactive proofs, where you're only going to be certain that you have the right answer with high probability. So this is a sort of a class of algorithms that maybe you wouldn't initially consider if you want to be right all the time, right? But if you're okay with only being right most of the time, with high probability you're actually right, then it opens up a much larger class of algorithms to you, where it might not be obvious how to see how they're fitting on this right-hand side of the branch. Okay, and so based on that intuition of the fact that, right, we are in this class that is naturally, that has some probabilistic flavor, and the fact that if we have that we're in both a class and its complement, that also hints that we should be able to do better. It's rare to find a problem that is in the class NP and co-NP that doesn't fall down to P. And lastly, right, we had some early conversations with Kevin, who I think is here in the audience, that hinted that maybe a probabilistic flavor of a solution could work to this problem. And so we decided to try even harder to try to get this sort of probabilistic solution to the problem. And we do. So we are able to remove this fancy computer science assumption, remove the GRH assumption, and we give a probabilistic polynomial time algorithm to actually decide if this Schubert coefficient is positive. Okay, and so this lands us in the class RP, which are the probabilistic polynomial time algorithms, where I could make an error, but I'm only going to make an error in terms of maybe I'll accidentally say the answer is no when the answer should be yes. Okay, but if I output a yes answer, that is 100% correct all of the time. And so let's give maybe an idea of how this would come up, right? And how is this one-sided error? Where is that popping up? And for our argument, we're really using two main ingredients. And so the first is a lemma of Kevin's that appeared in his work, where he was interested in investigating this Schubert vanishing problem. And he has this lemma that's saying, okay, my Schubert structure coefficient is going to be positive if and only if I have this sort of technical looking sum of vector spaces is actually a direct sum of vector spaces. Okay, where these are sort of coming up from the tangent spaces of these Schubert intersections. That's where this is sort of coming from. But these are UVW, you can think that they're going to be strictly upper triangular matrices, where you'll have free variables in the positions that are given by like the inversions of these permutations, something like that. Okay, and so then you are acting on these spaces by these generic invertible matrices. And this is saying that, okay, my coefficient is going to be positive exactly when this sum of these spaces is actually a direct sum. So this is giving some idea of this spanning as much as possible. Okay, so that's number one. Because, right, why is this a good formulation? This is really boiling down to linear algebra, which we can do quickly. Okay, so this was the right characterization to use. And then the second ingredient, which it might not be clear how this is going to pop up immediately, is this the Schwartz-Zippel lemma, which maybe you've seen in an undergrad probability class or something. You could prove this. And so what this is saying is, if I have a non-zero polynomial that has degree d, we could ask, what is the probability that when I plug in a point, I accidentally find a root? What is the probability that that could happen? And so this says that, okay, if I'm sampling numbers to plug in this set S, the probability that I accidentally find a root in S is going to be bounded above by D over the size of S. Okay. And so why is this helpful? Let's say I have a polynomial, and I want to know, is that polynomial zero, identically zero? Then maybe that polynomial would be too big to write down. But if I could just plug something in, if I plug something in and it's not zero, then I know the polynomial is not zero. But if the polynomial were zero and I plug something in, I should get it zero every time. And so that gives a quick test, right? But you could sort of get a faulty answer if you accidentally plug in a root. And Schwartz-Zippel is bounding how often that can happen. And so what we do is we first just restrict to the setting in which we could possibly find anything in the intersection, any points in the intersection. So we just restrict to those u, v, and w's that'll actually intersect in a zero-dimensional way. Second, we use Perbous's lemma to construct a matrix that's exactly going to have a non-zero determinant precisely when this coefficient is positive. Right, so we're going to construct a matrix that's going to be non-singular exactly when that sum of vector spaces is actually a direct sum. And so then we just have to tell when is the determinant of this matrix identically zero, and so we'll just plug in a random point and see if that determinant is zero, because it's easy for us to, once we've plugged in some entries in the matrix, it's easy for us to compute that determinant. And so lastly, we just use the Schwartz-Zippel lemma to determine what is the probability that when I did that random evaluation, I accidentally made the matrix singular if it was not before. And so using that, we get our probabilistic polynomial time result. Because if I plug in my random entries into this determinant and I get a number that's not zero, I know with 100% certainty that that coefficient has to be positive by the Perbous's lemma. If I plug in an entries into that determinant and I get zero, I might have accidentally made matrix singular, but the Schwartz-Zippel lemma bounds the probability of me accidentally sampling a root there. And so we get that probabilistic polynomial time result for our Schubert vanishing problem. And if we assume, again, a less strong computer science assumption that this bounded probabilistic polynomial time equals p, then we actually get a polynomial time result to test when our Schubert coefficient is positive. This also, for free, if you actually don't want probabilistic algorithms and you just want honest to goodness ones, this gives you an NP test for Schubert positivity, because, right, what would be your proof that we would check that the coefficient is positive? Well, if the coefficient is positive, there's going to be some evaluation of the variables I can make that makes this determinant non-zero, right? There's going to be some non-root there that I could sample. And so our certificate would be giving me exactly what I should plug in so the determinant is not zero. So as a corollary, we get the coefficients are in P. And I should say that the lemma that we use of Kevin's is actually stated for all classical groups and arbitrarily many intersections. So our algorithm actually holds for arbitrary classical groups and arbitrarily many intersections. So maybe you care about sevenfold intersections in the symplectic for the symplectic group, right? And our algorithm will also give you that probabilistic polynomial time result to decide whether those intersection numbers are positive. And I'll stop there. Thanks.
Questions for Colleen?
So how does this compare with the complexity of the same question for just ordinary Littlewood-Richardson coefficients? It's the only computational complexity question in combinatorics that I sort of have. Oh, Perry's answered.
Yeah, so it's in P, but there is there are many differences between the two. But for that P, right, our inputs are all in unary. But the Littlewood-Richardson case is actually proven to be in P even with binary inputs. So our algorithm, even if you wanted to use our algorithm for the Grassmannian case, the one that was already existing is far more efficient in that case. But again, it's yeah, in terms of Pear's question, computing Littlewood-Richardson coefficients.
Right. That was the factoid I was remembering, although I didn't think I could state the definition of the computational complexity class.
Yeah, but it's sharp P complete for inputs in binary, but open for you.
Is the hardness related to the fact this is probably not an answerable question, but do you get a sense that the hardness is related to the fact that we don't have these combinatorial rules, or is this just hard for a different reason?
It's hard for a different reason. So I mean, are you talking about the hardness for the Littlewood-Richardson coefficients?
Sorry, no, I meant your problem, right? Like we don't have a combinatorial.
Right. So that's sort of part of what we were, when we were initially setting out to do this, we were trying to prove that actually computing, getting any combinatorial rule, that it should be impossible too hard, right? And so if we could have proven that the decision problem, that just deciding if it's zero at all was hard, then that would sort of, as a result, show that the counting problem was hard. But then it just sort of backfired on us. That just wasn't the truth. So this sort of led us in a different direction, where it would be really surprising if the decision problem was as easy as it is and there was no combinatorial rule at all. So it's more likely that even if it isn't even if the Schubert counting problem isn't in sharp P, I think it's likely that it is in the counting hierarchy at this point.
Thank you.
So what do you think, Colleen, for the chances of actually getting like a human usable decision problem?
For the counting problem?
Well, no, at least for the zeroness question. Because
well,
currently it's basically in P, but it's pretty hard to pull off, right?
Well, you just write down a matrix and test if the determinant is zero. It depends what you mean by human.
Well, I mean me.
Because I mean, like, even for the Littlewood-Richardson, right, that's still using linear programming. It's still not, even as nice as it is, it's still not something that anyone's going to do on pen and paper, right? So all of these things, it's 0% chance that it's going to be something that, even unless it's something really small, that you're going to want to do on paper. And that's just, I think, the nature of the problems, really.
So for the counting problem, you sort of mentioned that I am not familiar with the state of the art, and this is what I wanted to ask about, because you said that it might not be in sharp P still, but showing that the decision problem is in NP suggests that it is in sharp P, right?
Not quite. I mean, right, you can have a problem where it's easy to find a solution, but it might not be easy to check any solution. Right? It could be a situation in which there's a greedy algorithm that will find some solution. And that is easy to apply, but it doesn't mean that it would be easy to check every solution. And that's where something bad could happen.
Yeah, but generally it's the type of it's the type of thing that suggests that it would be close to sharp P, right? So what's the best thing?
That's what I'm saying. So it would be unlikely that the decision problem would be almost in P, and that the counting problem would be not in any counting hierarchy. Like that,
right.
That's probably not going to happen. So it's a good sign with regards to that, but nothing so explicit. Yeah.
All right, let's thank Colleen again. Oh, sorry.
Here's a question.
Yeah, thanks, Colleen, again, I guess, while people are clapping. I guess I was just curious if you all had thought about it all, like if there's a quantum polynomial time algorithm for deciding Schubert positivity, or if that's something anybody's worked on.
We haven't looked at it just because I think this was sort of, I don't know, this is already quite good, if you're okay with being wrong sometimes. But right, if we sort of failed at having an efficient algorithm, then maybe we would have looked more towards the quantum.
Yeah, I guess it just sort of reminds me of the trajectory with like primality testing, where for a while we
Yeah.
had good randomized polynomial time algorithms, but then eventually, and then on the factorization side, which is also in NP intersect co-NP,
Yeah.
eventually there was a quantum polynomial time, but I don't know.
Yeah. But with integer
Excuse.
factorization, it seems like this problem is far nicer than that.
Okay.
And so I think maybe, yeah, but that is something that we haven't looked into it, but that's definitely something that you could, yeah.
Cool. Thanks.
Okay, so we'll save more questions for later. Let's thank Colleen.